All right, catalysts. Last part of this chapter talks about a very important part in our existence and nature's existence for that matter. A lot of the natural reactions that take place as an exothermic reaction. And exothermic reactions usually are what we call spontaneous. Let's put it that way. Meaning that there isn't much activation energy to get it going. Just enough to push it along, but the natural heat from the sun, or radiation from the sun, or the heat of the temperature within a room is usually enough energy needed to get the reaction going. But there's a fairly good number of reactions that won't work just under those conditions. And so they need a little extra kick in the butt to get going, chemically speaking. And that kick in the butt is called a catalyst. And the catalyst will knock down the amount of activation energy by giving a different route for the reaction to go. Instead of going from A to B, or A to C rather, it'll go to A to B and then B to C, because that route is a lot more easily taken than going from A to C. It's like you may want to drive, say, from one town to another, but the road has so many potholes in it and just takes forever with all the construction going on around it. It's just hard. So you take an alternative route to get there, and you get there a lot sooner using that alternative route. It may have been longer, but it gets you there. It's kind of the same thing with catalysts. The human body has a series of many reactions that take place that require catalysts to take place. We don't call them catalysts because in organic chemistry or biochemistry, they have a specific name, and that name is enzyme. Okay? We have a number of enzymes to break down food that we consume. If they don't, then the food will just go straight through without being broken down. We'll starve. We need to have the nutrients supplied all around the body for various parts of it. So the types of food that we consume, there are specific proteins that are geared to fit into the shape of the protein that they're trying to break down. Proteins or chemical compounds actually do have shapes. We talked a little bit about it in Chem 1 with the Vesper theorem, or Vesper principle. But it's even more engaging than that. I mean, the shapes are literally like a moon with cavities in it or something. It's just really weird. And so, but in order to break that down, you got to have something that's going to connect to it and then allow the collisions to occur to make that break down. And that is a very specific thing. Those enzymes are also called lock and key compounds, where they fit like a lock and key together to hold the compound while collisions are made to break it down. And without those collisions, we can't break down the food, we can't get the nutrients to wherever. Other reactions require things to occur that wouldn't occur without it, like getting rid of, moving the water around in different parts of the body. The result of a lot of chemical reactions, which is water, is going to be involved in that. The removal of the waste also involves a chemical process, a filtration process. There's all kinds of biochemical catalytic things that allow these things to occur. If they don't occur, we die. So this is extremely important. These reactions keep us alive. Okay, so in the script I go through a number of options there, particularly the enzyme for dairy products. That is called lactase. Comes from lactic acid, which is the acid that you smell in milk when it goes bad. So lact means milk, which is what dairy products are. It comes from in milk. The ACE tells you you're dealing with an enzyme, a catalyst that's going to allow to break down those foods. Lipase for fats. The lip comes from lipoid compounds, which are fatty compounds. So to break down the fats, that enzyme is used to lock in and break that down as well. Proteins are broken down with something called protease. You can see the name of that. These all work really well. But there are two types of catalysts. There are homogeneous catalysts and heterogeneous catalysts. And the enzymes that I'm talking about there are homogeneous catalysts. They are the same phase. They look like they're part of the solution. They're all in there. But it's not exactly homogeneous like we talked about in Chem 1, where everything looks the same. It means they're in the same phase. Okay? So a homogeneous enzyme would be a solid attaching itself to a solid to allow the particles to get broken down. They don't look the same, but they, in fact, sometimes are mirror reflections of each other, and sometimes not. Another example is a heterogeneous mixture, or a heterogeneous catalyst, and the catalytic converter is a really good example of a heterogeneous, because in that we have an ability to break down not break down carbon monoxide, but transform carbon monoxide, which is produced in inefficient burning of the car, into carbon dioxide, which is what it should be in a complete burning of the gasoline in the car. But because all engines are inefficient, you get byproducts that you are not supposed to get. Carbon monoxide is worse, and as you know, carbon monoxide is a lethal poison. Not like carbon dioxide isn't poisonous, but it is not as poisonous as carbon monoxide. And of course, carbon dioxide certainly has this issue as well, but we'd rather deal with those and try to fix them than try to fix the problem of having too much carbon monoxide, which will kill us. So they put a piece of metal into kind of like a box attached to the exhaust system. The exhaust has to go through, goes into this, and then comes out. Well, in that box, what you want is to have the oxygen in the atmosphere collide with the carbon monoxide to produce carbon dioxide. It won't do it. It just won't do it. So you put a little piece of metal in there that'll hold carbon dioxide and allow the oxygen to, remember this is very hot, so that means they're moving very, very quickly, hanging away over there until they get a reaction take place, and then it loses interest in it because of electron affinity or the lack thereof, comes off, it gets removed, and then another carbon monoxide gets stuck on there. And it turns out that the metals that work really, really well, the ones that don't get disrupted by heat, and they don't corrode by reacting with the stuff around it. Gold and platinum are the two most favorite catalytic converter substances. This is why catalytic converters cost a tremendous amount of money. I used to own a little putt-putt car called a Sprint. A little Sprint had a problem with catalytic converter. I accidentally had somehow got water into the exhaust pipe and then it encrusted everything up in my catalytic converter, so it had to be replaced. Now, this is just after catalytic converters came out. I had no idea what it was made of until I got the bill. Oh boy, did I ever learn how much what was in there. It costs, for a little putt-putt car, about not even $3,000, it costs $750. I said, what is it, made of gold? He said, yeah, it's made of gold. No, well, here's the $750. Anyway, let's take a look at the potential energy chart of a chemical reaction with and without a catalyst, shall we? So, we got this thing here, and as we said, this is going to be the energy, and this is going to be the time in which the reaction takes place. And let's take a look at an exothermic reaction, which means you'll start up high and you end up down low. Now, if you have, let's say the reaction is A yields B, about as generic as you're ever going to see. So A is going to be here, collision is going to go with A, we're going to produce B over here. It's not a really good reaction to run on its own. It takes a lot of energy to get it going. So we're going to give it a lot of activation energy. So this is very high activation energy. Okay? We can get this to go if we can find some catalyst, like say a piece of platinum or gold, and decrease that activation energy, and so it'll look something like this. So just very tiny amount of activation energy. And again, that activation energy can just come from, radiance from the sun, or just the temperature flow, which is radiance as well. And that's enough to get it going, and boom, there it goes. Yay us. That's what a catalyst does. It changes the direction of the reaction. So instead of going direct from A to B, it goes to another point, stuck on a metal, forcing me to collide with it, and then there we go. No metal, or no catalyst, no reaction. Okay? Now let's take a look at the same thing with an endothermic reaction, which needs it even more. This time we'll plateau over here, and we'll put it up here. And energy and time. Now, you take, for example, what goes on with trees and grass and all that, where you have all these greeneries. That is really, well, you know what photosynthesis is. It's the capturing of carbon dioxide and water from the outside, processing it, and forming food for the trees in the form of glucose, and the residue, the stuff it doesn't want, is the oxygen, which we want. Yay us! Save the trees. Hint. Well, this is an example of an endothermic reaction. So, in fact, this is probably not even showing how extreme the catalyst is, and they think that they're not sure, but I think they're coming to a point where they think they may be able to reproduce this in the lab. But it has to do something with either a magnesium or a beryllium or some complex involving both that act as a catalyst. But you got this thing going on right here. This thing just does not want to react. But if you put the magnesium beryllium complex in there, you're going to get this kind of thing right here. Virtually very teeny tiny amount there, but the actual activation energy is from here to here, which again you can get from the sunlight. Remember, sunlight allows the trees to make their food, their glucose. So the absorption of the sunlight is there, but when you have this much, the absorption of the sunlight isn't enough. So the magnesium beryllium complex here. So like when you talk about the delta H, which is right here, this is positive. The EA is always positive, but it becomes less positive here. Less positive EA, but it's always positive. If we go back on top over here, the delta H is right here. For exothermic reactions, that's negative. The activation energy is always positive. But this is, EA is hardly positive. Let's just put it down. It still has to be positive, but it doesn't take very much to get it going. And that is the difference. So when you do the problems, keep that in mind as you go through them. Speaking of problems, here are your two practice problems. Number one, this scenario right here, and number two, this scenario right here. In both situations, you are to show both reactions with and without the catalyst. So label catalyst for one and label no catalyst for the other, for both of the two different problems. Okay? Good luck.